The nice thing about an open-ended example like this is there's lots of ways of taking what we've done further in a number of different directions. For example, you might, well, I didn't talk about how to do simplification, that you can just over expressions, you can simplify things without evaluating them. You could add more operations like subtraction, division and remainder and so on. You could extend the language to allow setting variables or defining functions for yourselves, or even adding other types like booleans. You could also do things, you could change the syntax. At the moment, we have to fully parenthesize everything. You could have operator precedence implemented. Now this would change the parsing algorithm, for example, but you could, so that if you saw something like 2 plus 3 times 4, you'd know to do the 3 times 4 first and then add 2 to 12. So there's a whole lot of ways you can take this further. Let's look at simplification just as a simple example. If we have add E1 and number 0, we can just say, well, simplifying that's the same as simplifying E1. We can get rid of the num0 addition. We can get rid of a multiplication by num0 by num1. That simplifies to E2. We can really simplify a multiplication by 0. That just becomes 0. So there are those simple cases. It's more complicated in the case of an add. What we'd like to do with add is simplify both halves. So here S1 is the result of simplifying E1, and S2 is the result of simplifying E2. Then we'd think the answer might be add S1, S2, but that's not going far enough. We want to simplify that result because it may be that S1 is itself num0, so we could then simplify that top level addition of a 0. But if E1 and E2 didn't simplify, and S1 and S2 equaled E1 and E2, and we simplified again, we just go around in a loop. So we have to check that we've done some simplification either for E1 or for E2 or for both before we re-simplify at the top level. So that's why you get that complication at the end. That makes it a nice example. Okay. We talked earlier about verification a little bit when we talked about the ASCII art example, and we talked about how map and reverse we can apply in either order. So in general, we can apply that same approach here. And one thing that we'd love to prove is that if we evaluate an expression using our evaluator, and we also compile it and then run it, we would expect to get the same result. And we can write that as this simple equation. On the left, we've got eval, on the right, we've got run, starting with the empty stack. So we would hope that for all expressions and environments, we should be able to prove that. And we would prove that using induction. Another thing we'd like to do is to see that printing and parsing are reverse operations. So if we start with an expression, we print it out and then parse it, we would expect to get the same expression back with an empty string in the second half of the answer. So on both sides, we would expect to, and I think we would expect that if we did the print and the parse in the opposite order, we would expect them to behave in the same way. So we can write proofs of this form so that we get the results for every possible value of expression. Now, of course, we could also write tests for this, and we could also do property-based testing. So we could generate random expressions and environments and check that these properties hold in 100, 1,000, whatever number of random test cases we would like to do. And as I said, to do the proofs, we would use induction over exp. And that's induction is for proof, like recursion is for definitions. We prove the result for complex things, assuming the results already hold for their subcomponents, and we'll look at that later on in the course. So what have we learned? What have we learned in this module? We've learned something about how we can represent data using type definitions and data definitions, and those help us to structure our approach to this problem. We think about the types first, and once we've got the types and the types of functions, as we developed in the parsing example, we can then think about writing the definitions themselves. We've used pattern matching throughout, different kinds of pattern matching. We've used different patterns of recursion. We used direct recursion. We used tail recursion on when we were looking at how to define the run function for the virtual machine. We used a form of tail recursion in the parsing algorithm. So we've seen different approaches brought together to work in this single example where we're dealing with expressions, transforming expressions, simplifying them, running them, turning them into strings, and also turning strings into expressions.